Good morning to one and all. So in the session number 9 we are going to discuss about class B push pull amplifier. So this is a subtopic comes under unit 2 BJT biasing and amplifiers. So first let's discuss what all the topics we are going to discuss. So in this session we are going to discuss about class B push pull amplifiers, the construction, working and advantages and disadvantages of class B push pull amplifiers. Similarly, we are going to discuss about complementary push pull class B amplifiers also, how exactly it works, how can we design the circuit, and what all the uses and the drawbacks of these class B push pull amplifiers. So in the previous sessions you people have already learned about different types of power amplifiers. That means power amplifiers are classified mainly based on the conduction angle. So based on the conduction angle, the power amplifiers are classified as class A amplifier, class B amplifier, class C amplifier and class AB amplifier. So the difference, one of the main difference what you learned in the previous class is about the class A. There the conduction angle is 360 degree. That means output will be appear for complete half cycle of the input signal. Whereas coming to today's class, it's about class B amplifier. So the class B amplifier, the conduction angle is 180 degree. So when the conduction angle is 180 degree, then the output will appear only for half of the duration of the input signal. Whereas in the class A, the conduction angle was 360 degree. When the conduction angle is 360 degree, we will get complete output cycle. So the output is appear for complete input will be appear at the output side with an amplified version. Whereas here in case of class B amplifier, the conduction angle is 180 degree. When the conduction angle is 180 degree, transistor will be on for only half of the duration of the input cycle. The active element will conduct only for 180 degree. Whereas in case of class A amplifier, we already studied it's a single-ended amplifier. In a single-ended amplifier, it will introduce some types of distortion. So the distortion is due to non-linearity of dynamic characteristics of transfer characteristics of the transistor. So and again in these push pull amplifiers, which has an output stage that can drive the current in either direction through the load. That means here in the push pull amplifier, at the output stage we will get complete output, but that some changes we did in the circuit. So to get the entire output we are using push pull amplifier. See why we are using this push pull configuration means in the first sentence it is mentioned clearly that the conduction angle is 180 degree. The conduction angle is 180 degree, but we required complete cycle of the output. So for that purpose we are using this push pull configuration. So how exactly we will get complete cycle of the input even with a 180 degree of conduction angle, in the next slides we are going to discuss. The output stage of typical push pull amplifier consists of two identical BJTs, bipolar junction transistors. One BJT sourcing the current through the load while other sinking the current from the load. That means with the conduction of angle of 180 degree only, we have to produce 360 degree of output. That means complete output we should get. So for that purpose what we are using? We are using two transistors. See there one of the sentence is very important. There they mention we should use two transistors with identical characteristics. That means they should have a similar characteristics. What will happen if I am not using similar characteristics? So that we will discuss in the coming slides. So here what is the purpose of two BJTs? They mention one BJT for sourcing the current through the load, that means to transfer the current through the load, and second one is sinking the current from the load. These transistors, these push-pull class B amplifier transistors, they are used where we require low distortion, high efficiency and high power output are required. And these push-pull amplifiers are superior, that means they are better compared to what? They are better compared to class A amplifiers. They are saying push-pull amplifiers are superior or better compared to class A amplifiers. So in terms of what? In terms of distortion and performance. So the class A amplifiers is using one transistor. Class B amplifier push-pull configuration, we are using two transistors with the identical characteristics, and these class B push-pull amplifiers are superior in terms of distortion and performance compared to what? Compared to class A amplifiers. Next, construction. See, the construction point of this class B push-pull amplifier is very important in terms of your exam point of view, because you will get a question like this: explain the construction of class B push-pull amplifier, like that. So what are the, how exactly we can mention the construction details and all? First, the class B push-pull amplifier consists of two transformers. If you observe the diagrams here, they clearly mention it consists of two transformers. So transformer T1 and T2. Now the transformer T1 is, we can call it as input transformer, or you can call it as splitter transformer also. I will tell why exactly why it is called splitter transformer. So it is input transformer, and here where we are applying the input signal, so transformer will have primary windings and secondary windings. So we already knows in the we already learned in the basic topics. So the transformer, the input transformer, the primary of the input transformer terminal, we are applying the input signal. See, this one you should write very carefully. That means we are applying the input signal to the primary windings of input transformer, and we are taking the output from the secondary windings of output transformer. So here we are taking output from secondary winding. Here we are applying the input to the primary windings. So that's why transformer T1 acts as a input transformer, or it is, I also mentioned the word, it is called splitter transformer. So why I am saying it is splitter transformer? Let us discuss first. So this transformer, the transformer T1, if you observe the diagram of transformer T1, it is like center tapped transformer. Now this center tapped transformer, what exactly it will do means, whenever I am applying an input signal to the primary windings of transformer T1, so these transformer will produce two sinusoidal signal with a opposite phase angle. That means it will produce two sinusoidal signal with 180 degree phase shift. If you observe here, for the transistor Q1, for the base terminal of transistor Q1, we are applying one of the input signal, and at the same time for the base of transistor Q2, we are applying one more sinusoidal signal. The difference between the signal which we are applying to the base of transistor Q1 and base of transistor Q2 is, both are 180 degree to 180 degree phase shift to each other. So we are getting two signals with 180 degree opposite phase, that is because of this splitter transformer, or we can also call it as this one as splitter transformer. This center tapped transformer will produce these two signals. And next one, the two transistors whatever we are using, the emitter terminals. See, the transistor Q1 emitter terminal and transistor Q2 emitter terminal, they are connected together. That is the second point. And third point, the center tapped terminal of the primary transformer. So the center tapped terminal of the transformer T1 and the negative terminal of the power supply, they are connected to a junction where two emitter terminals are connected. I repeat again, the center tap terminal and the negative terminal of power supply, they are connected to the point where two emitters of transistors are connected. And next point, the collectors of Q1 and Q2, if you observe, see in the diagram, the collectors of Q1 and Q2, where they are connected, the collectors of Q1 and Q2, they are connected to the primary windings of secondary transformer. So the collectors of Q1 and Q2, they are connected to the respective terminals of primary windings of transformer T2. And what is connected to the secondary of transformer T2 means the secondary of the transformer T2, the load is connected. So this is what the construction diagram. So input is applying to the primary of the transformer T1 and it will split the signal and it is applied to the base of two transistors Q1 and Q2. Emitters of two transistors are connected and to that junction center tap terminal and negative terminal of the power supply is connected. The collector terminals of two transistors Q1 and Q2, they are connected to the respective terminal of secondary transformer primary windings, and load is connected to the secondary transformer secondary winding. Next, these are the things what I already explained. The push-pull circuit requires two transformers. Yes, one as input transformer, we also call it as driver transformer, and other connected to the load called output transformer. So T1 is nothing but input coupling transformer, where we are applying the input again to the primary terminal. Q1 and Q2 are identical transistors, their emitters are connected. Yes, and again I already mentioned the center tap of input coupling transformer and negative end of voltage source is connected to the junction point of emitter terminals, and positive end of voltage source is connected to the center tapped of coupling transformer and output coupling transformer. See here, negative terminal is connected to the junction point of emitter, whereas the positive end of this power supply is connected to the center tapped output coupling transformer. And here the collector terminals of each transistors are connected to the respective ends of primary and secondary, and finally the load RL is connected to the secondary of transformer T2. Yes, now we will discuss about the working principle, how exactly it works. See, the transistor Q1, Q2 both are operated in cutoff. That means that they are class B amplifiers. Their operating point is exactly lies at the cutoff region. So this is one of the benefit actually. When there is no input signal is applied, suppose assume that when we are not applying any of the input signal, when we are not applying any input signal to the transistors Q1 and Q2, will not take any power from the VCC, and there is no power loss. See, this is the one of the best advantages of class B amplifier. That means the efficiency of the class B amplifier is more as compared to class A. So what is the reason means the class B amplifiers are operated in the cutoff region. That means the Q point is located in the cutoff region, when there is no input signal is applied, at that time transistor will not take any power from the VCC. When there is no input signal is applied, there is no power loss. So when there is no input signal is applied, there is no power loss. This increases the efficiency of the transistors. When an AC signal, next case, what will happen when I am applying AC signal? When an AC signal is applied to the input terminal of push-pull amplifier, that means transformer T1 primary windings, the primary windings of transformer T1, we are applying an AC signal. When an AC signal is applied to the input terminal of push-pull amplifier, then for each off cycle of input signal, again I am saying, for each off cycle of input signal, one transistor is pushed into conduction mode and other transistor is pulled out of conduction mode. That means in this push-pull configuration, both the transistors will not turn on or turn off simultaneously. One transistor is pushed into conduction mode, other transistor is pulled out of the conduction mode. So which transistor on which half cycle we will discuss. First, the signal to be amplified, it is applied to, already we discussed, it is applied to primary windings of input transformer. The signal to be amplified is first split into two identical signals of 180 degree phase by transformer T1. Next, these input signal is splitted into two 180 degree phase shift signal by this center tap transformer, and they are applied to base terminal. Again I am saying they are applied to the base terminal of transistor Q1 and Q2. In the diagram it is shown here, transistor Q1, they are applied the signal with 0 degree phase shift. That means the signal will start with 0 degree phase. Whereas the signal which we are applying to transistor Q2, it is exactly 180 degree shifted version of the input signal. That means they are exactly the base of the input signal, whatever the signal we are applying to transistor Q1 and Q2, they are 180 degree opposite phase. Next, what will happen? The transistor Q1 conducts for positive half of the input cycle, producing positive half cycle across the load. See what will happen in the previous slide. If you observe here, transistor Q1 we are applying an input signal with a 0 degree phase shift. When I am applying this signal, transistor Q1 will be turned on. That's what they are saying. Transistor Q1 conducts for positive half cycle. And one point you should be remember that transistor Q1 is only conduct during positive half cycle. So that's why transistor Q1 conducts for positive half cycle of the input signal and output will be appear the positive half cycle. So what will happen to the other transistor during this condition? That's what they mention. While the transistor Q2 conducts for negative half cycle of the input, that means during the positive half cycle, transistor Q2 will be pulled out of the conduction mode. That means they are off. During the positive half cycle, Q1 will be on, Q2 will be off. Q1 will be pushed into conduction mode, Q2 is pulled out of the conduction mode. Whereas exactly the thing will be reverse. During the negative half cycle, transistor Q2 will be conduct and Q1 will be in the off condition. That means Q2 is pushed into conduction mode and Q1 is pulled out of the conduction mode. So one thing we can summarize from these 2 points, during positive half cycle one transistor will conduct and other will be off. During negative half cycle one more transistor will be conduct and the remaining transistor will be off. So simultaneously one of the cycle one transistor is conducting. So that's why at the load we will get a complete full cycle of the input cycle. So that's what they mention. The waveform induced across the secondary is similar to the original input signal. but it is amplified, that's what. So because it will be amplify the input signal. But the important point here is, even though we are using class B amplifier, the conduction angle is only 180 degree. Even though the class B amplifier conduction angle is 180 degree, but still at the output cycle, that means at the load, the complete input signal will be appear. That is because of two transistors we are using, that too with the push-pull configuration. So this pushing and pulling effect of alternating half cycle by the transistor gives the name as push-pull transistors. So what is the advantages? High output power and efficiency. As we already discussed, efficiency, one of the reason why efficiency will be high means when there is no input signal applied, none of the transistor is on, that means transistors will not take the power from VCC, there is no power loss, so efficiency will be high, and this will reduce the non-linearity of transfer characteristics of single transistor amplifier, because in the single transistor amplifier non-linearity will be there. So that problem we are overcoming here. And as I already mentioned, very important point, when there is no input signal, power dissipation is zero, and transistors are biased at cutoff point. See, that's what, this is very important point. In case of push-pull amplifier, the transistors are biased at cutoff point, they consume no power during the ideal condition. And last one, the advantages here is, we are using the transformer at the input side of the amplifier and at the output side of the amplifier, so that's why transformer we can use it for impedance matching also. And what are the drawback? Obviously, one of the major drawback of this one is the two transistors. In the beginning, in the construction part, I explained the two transistors should be of identical type to produce equal amplification, because in a sinusoidal cycle, one half of the output cycle is because of amplification factor from one of the transistor, and other half of the cycle is the contribution from the other transistor. When we are not using the similar transistor, obviously there will be the mismatch in the amplification factors of output. So that's why two transistors should be identical, and center tapping is required for the transformer, because the input signal we have to split into two 180 degree phase shift signal. And because of usage of transformer, they are bulky and costly, and circuit gives more distortion and all. So these are the drawback of class B push-pull amplifier. Now with this summarization, we can say that class B amplifier, push-pull amplifier, they require the transformer, they require identical transistor. Now next topic is complementary push-pull amplifier. So what is the need? So the need of complementary push-pull amplifier is the drawback of normal class B push-pull amplifier. So that drawback we are overcoming by implementing this complementary push-pull class B amplifier. So here what we are doing, the class B push-pull amplifier improves the efficiency. Obviously it improves the efficiency as compared to class A amplifier. See how much efficiency of class B amplifier, class A amplifier, that one we will discuss in the next session. We will calculate the power efficiency of class A and class B amplifier. There exactly the numerical value we will calculate. But the time being, I can say that class B push-pull amplifier efficiency will be high, but the center tap transformer will make that circuit becomes costly, bulky and heavy to construct. So that's why, to overcome this limitation, class B push-pull amplifiers can made into complementary symmetry class B amplifier. So what they are using? They are not using transformer here. So that's why it is transformer less amplifier. So this circuit is using, instead of transformer, they are using complementary pairs of transistors and that's why they are calling as transformer-less class B push-pull amplifier. And there is no stray magnetic effect because transformers are not using, so that's why there is no stray magnetic effect. So how exactly the complementary push-pull amplifier? So the complementary push-pull amplifier, the circuit whatever it is shown here. So in this circuit, if you observe here, the input signal is applied. Here we are using two transistors. If you observe the diagram very carefully, the one of the transistor is NPN transistor and second one transistor is PNP transistor. Now the NPN transistor arrow mark will be outward from the transistor, and PNP transistor arrow mark will be inward. Now the name, why the given name as complementary? They are given the name as complementary. The reason is one of the transistor is NPN and other is PNP. So both the transistors are complementary to each other. Whereas in the previous slides we discussed that push-pull amplifiers, two identical transistors are required. So what will happen if I am not using two identical transistors? Obviously the amplification factor may not be the same. So if amplification factor may not be the same, so obviously we will not get the proper output. That means similar kind of output. So that's why here that problem is overcome by using two transistors. They are not identical. One is NPN and second one is PNP. But remember one thing, here they are saying complementary transistors. But complementary transistors, they are, one is NPN and second one is PNP. But they should made of same material and they should have same power rating also. Again, if you are not using same material transistors and same power rating configuration and all, so the same problem will be appear. But time being here, two identical transistors, that problem we are overcoming by using complementary symmetry. And next one, we are applying input to the Cin, that means it's a coupling capacitor. So what is the benefit of this coupling capacitor we will discuss. And here we will discuss about we are using four resistors R1, R2, R3 and R4. So what are the benefit of these resistors and all, we will discuss in the next slide. So first what we are doing, the input signal is applying to coupling capacitor, then we are using two transistors. So here we are using one transistor as NPN transistor and second one as PNP transistor. So obviously the arrangement of two transistors having complementary symmetry, that means they are opposite. One is PNP and second one is NPN. So here complementary symmetry transistor, as I already mentioned, they should made with a similar material. That means they should made with the similar material and technology with the same maximum rating also. So that is important factor here. Next, here Cin is nothing but coupling capacitor that couples the input to the base of both transistor Q1 and Q2. So what is the benefit of using Q1? We will discuss. So the Q1 is nothing, what is the benefit of Cin? So Cin is a coupling capacitor that blocks the DC component of input signal. When it blocks DC and allows only AC signal, so that benefit is nothing but it is not having any power dissipation when there is no input signal is applied. So that is the meaning. That means Cin is nothing but coupling capacitor that is used to block the DC component, or in the other way I can say that it allows only AC component. So in that case, during zero input signal, that means when there is no input signal, there is no power loss. That is because of coupling capacitor C1. Resistors R1 and R2 provide voltage divider bias. So we already know that voltage divider bias is one of the technique, is one of the biasing method. So that is used for R1 and R2 is used for transistor Q1, and second was similarly resistors R3 and R3 provide the voltage divider bias for the emitter base junction of transistor Q2. And the resistors are so selected. While selecting the resistors, we should choose the value of resistor such that the operating point should be in the cutoff region, because here we are using class B amplifier. So class B amplifier, they are operated in cutoff region. The Q point will be exactly at the cutoff region. So that's why while selecting the resistors value, you should be very careful about the resistor value such that the operating point should be at the cutoff region. So when there is no collector current flows under no signal condition, that will improve the efficiency. Working principle, how exactly it works. The signal applied to the input is fed to the base of both the transistor, correct? So what we are doing, we are applying a signal that is given to both the transistors. Two transistors conduct in opposite half cycle of the input signal. So here what will happen, simultaneously I am applying the same signal to the two transistors, whereas in case of in the previous class actually whatever we discussed, there the transistors whatever the input signal we are applying to the base of two transistors, there we are applying a signal to the transistor Q1 and Q2 with opposite phase in case of class B amplifier. Whereas here in case of class complementary symmetry, we are applying a same signal to the both the transistors. When we are applying a same signal to the both the transistors, during positive half cycle only NPN transistor Q1 is forward bias and it will conduct, whereas during the negative half cycle transistor PNP is conduct. That means during the positive half cycle NPN transistor Q1 is forward bias and it conducts. During PNP while PNP transistor Q2 is reverse bias during the positive half cycle. That means during the positive half cycle NPN transistor forward bias, PNP transistor reverse bias. So NPN transistor forward bias Q1 conduct and PNP transistor reverse bias Q2 is off. So at the output, at the load, output signal is appear, that will appear through the NPN transistor because that is in the on condition. Exactly reverse during the negative half cycle. What will happen in the negative half cycle? Similarly in the negative half cycle PNP transistor is forward bias and NPN transistor is reverse bias. So that's what we discuss. At one half of the input signal only one transistor will be on, either PNP transistor will be on or NPN transistor will be on. But obvious the result is at the output we develop complete cycle of input signal, so it will be appear at the load resistance. The reason why complete input signal appear at the load resistance is nothing but due to usage of push-pull configuration. That means one transistor conducts during positive half cycle and other transistor conduct during negative half cycle. That's what they mention. During a complete cycle of input, a complete cycle of output will be developed because of contribution from NPN transistor and PNP transistor. And what is the benefit of this class B push-pull amplifier, complementary symmetry? First point is we are not using transformer. When there is no need of transformer, obviously weight of the circuit will be less and it is compact also. When it is compact form, we can develop on IC, that means integrated circuit. So it is transformerless, it is not bulky, that means it's lightweight, and it is compact also. And here we may not require equal and opposite input signal because here we are using NPN and PNP transistor, so opposite signals are not required. Only similar signal we are applying, but they are conducting in opposite half cycle. What are the drawback? So the drawback is it is very difficult to get a pair of transistor. That means NPN and PNP transistors we will get, but the similar material, similar characteristics, there will be slight mismatch. So that's what they are saying, it will be it is one of the disadvantage. And here harmonics will be developed if there is any unbalance in the two transistor. That means, as I already mentioned, two transistor, they are complementary, but they should be symmetry. They should have made up of same material and same maximum power rating. If there is a mismatch, some harmonics will be produced. If the parameters of the two transistors are not same, obviously unequal amplifications will be there. So that is also drawback of this complementary symmetry push-pull amplifier. Next we discuss about crossover distortion. See, as your exam point of view, the class B push-pull amplifier is very important. There they may expect the question about, you may expect the question about construction of class B amplifier, push-pull amplifier, or complementary symmetry push-pull class B amplifier. And this is also one of the very important topic, crossover distortion. See, this distortion is occur mainly in class B amplifiers. Again I am repeating, crossover distortion, it's a problem that occur in class B amplifier. So when it will happen, distortion occurring where the signal changes from positive to negative or vice versa. That means whenever the signal, there is a change in the signal from positive to negative and negative to positive, during the zero crossing, only the crossover distortion happens. So why exactly it happens? Here they are saying two transistors we are using in push-pull configuration will have unique cutoff bias arrangement. Yes, we are using two transistors, one for producing the upper half cycle and other for producing the negative half cycle. That means during positive half cycle one transistor conduct, during negative half cycle other transistor will conduct, but unfortunately they are biased in the cutoff region. That means one transistor conduct for the positive half cycle and it will turn off once it reaches the zero crossing, and second transistor will start conducting from the negative half cycle after the zero crossing. So what exactly here is, when one transistor turns off, other transistor cannot begin conduction immediately. This is what I am saying here. Two transistor will conduct. There will be switching from conduction from one transistor to other transistor. But the problem is, when one transistor turn off and other start conducting, there is a gap actually. So this gap will causes the crossover distortion. That's what they are saying. When one transistor turn off, other transistor cannot begin conduction immediately. So both the transistors remain off for short duration, due to which output current becomes zero. So that's what they are saying. What they are saying, when there is a switching from one transistor to other transistor, there is a short gap between two transistor conduction switching time. So this causes output to become zero. So that is called crossover distortion. So I think in the next slide there is a diagram here. See what exactly happened here. If you observe this sinusoidal signal, so during the positive half cycle, after a certain point here, the output will be similar to input, and even negative half cycle also output is similar to input. Whereas this region, if you observe, see, input signal is sinusoidal, complete sinusoidal, whereas the output signal is not complete sinusoidal, because this is the region where both the transistors are off, because one transistor conduct for half duration and second transistor conduct for another half duration. But because of the biasing and all, for certain duration of time both the transistors cannot be on. So that is causes the crossover distortion. So that's why if you observe here the characteristics also, this transfer characteristics, see, one transistor starts conduct after this cut-in voltage. So this over the 0.7 voltage, if you are saying the silicon material and all, it starts conducting after this, and second transistor starts conducting after this again negative cut-in voltage. Whereas these point output will be zero, even though some input will be present, but still output will be zero. So that's why instead of complete sinusoidal signal, we are getting the signal with a distorted form. So this distortion we will call it as crossover distortion that occurs mainly in class B push-pull amplifier. This is very important point. Then we will find the solution how exactly we will overcome this class B push-pull amplifier. The problem of this is crossover distortion. That one we will discuss in the next class. And this is what already I mentioned. Crossover distortion produces non-linear transfer characteristics. Yes, here the transfer characteristics is not linear. And second one, this effect sensitive to smaller input. Yes, when the input signal is very high input signal, these this crossover distortion will not have any effect. Whereas if the input signal is smaller input signal, no, that will affect crossover distortion. That's why they are saying this is very important. This is sensitive to smaller input signal. So this problem can be overcome by pre-bias of the transistor. That is, there is no bias at zero cutoff point. That means they are saying zero cutoff point should not be, operating point should not be at zero crossing. That should be above the zero crossing. So how exactly we will overcome? Class A amplifier can be used to overcome this problem. So this one we will discuss in the next session. So here we will discuss some of the multiple choice questions which are related to this session. First one, which of these is incorrect for complementary symmetry push-pull amplifier? So we discuss about complementary symmetry push-pull amplifier. Let us discuss which is incorrect. They are saying incorrect incorrect sentence. So you people can guess the answer. First option, they are saying during positive half cycle NPN transistor conducts. Yes, this is during positive half cycle NPN transistor conduct. It is easier to fabricate on IC. Obviously it can be easy, it will be easy because we are not using transformer. The size of the transformer required reduces. And last one, they are saying efficiency and figure of merit are same as transformer coupled push-pull amplifier. See, the answer for this one is the size of the transformer required is reduces. That means here we are not using transformer only. So what is the point of reducing the size of transformer? So we are not using transformer in case of complementary symmetry push-pull amplifier. Whereas it will conduct for positive half cycle of NPN transistor conduct. That is correct. You can fabricate on IC, and again the figure of merit and efficiency will be similar as transformer coupled only. So the answer for this is C. Second question. So in push-pull amplifier, usually biasing is not required. Yes, it's very important question and very useful question also. In push-pull amplifier, biasing is not required. So why biasing is not required? So you can guess the answer for this question. And the answer for this question is transistors are working in class B operation. So when the transistors are working in class B operation, the operating point is situated at the cutoff region only. So it's indirect. That means they are working in class B operation amplifier. We are using class B amplifier, so that's why biasing is not required. Heat sink is used with the transistor. Power transistor do not require biasing. DC battery VCC is employed. So the right answer is transistors are working in class B operation. And third one, the drawback of push-pull class B amplifier. I think we have discussed in the first topic only, that in the beginning of the slide. So the drawback of push-pull amplifier, that's why we are moving to complementary symmetry. So I think now we can guess the answer. So the answer is amplifier circuit becomes bulky. Yes, class B amplifier, transformers are present, so obviously it will be bulky. And 2 identical transistors are required. Yes, that is also correct. So the right answer for this is both of the above. That means in class B push-pull amplifier, the drawback is amplifier circuit is also bulky and 2 identical transistors also required. So that's why the right answer is both of the above. Next one, a 2 transistor class B power amplifier is commonly called dash amplifier. I think it's a direct question. You can guess the answer. Yes, the answer for this one is 2 transistor class B power amplifiers are called as push-pull amplifier. So the answer is B. Yes, I think this is a direct question. Crossover distortion is a problem in which type of amplifier? Yes, you can guess the answer. Yes, the answer for this one is crossover distortion is problem in class B amplifier. See, here I am saying crossover distortion is a problem in class B amplifier, but in the last slides I mentioned it can be overcome by class AB. Here they are not asked about how to overcome. Here saying in which amplifier it is distortion will appear. So answer is class B. Yes, thank you one and all.